Theoretical digital logic defines a state change as instantaneous. A signal transitions from a logic 0 to a logic 1 in a perfectly vertical line. In practice, these transitions are governed by the physical displacement of electrical charge. Every logic gate functions as a circuit designed to fill or empty a load capacitor to register a new logical state. This process creates propagation delay, the time required for the voltage curve to cross a designated voltage threshold, like the VDD/2 midpoint. The rate at which these capacitive loads can be manipulated sets a ceiling on the maximum switching frequency of any digital processor. A standard CMOS inverter uses a PMOS and NMOS transistor to drive an output node connected to a load capacitor. When the input goes high, the NMOS network turns on, providing a conductive path to pull stored charge out of the capacitor to ground. The NMOS is used for this discharge phase because its source is fixed to ground. This keeps the gate-to-source voltage high, allowing the transistor to drain the capacitor voltage entirely to 0. When the input drops low, the PMOS network activates. This initiates the charging phase, pumping charge from the supply voltage into the capacitor. PMOS transistors are used for this pull-up operation because they can drive the output node to the full supply voltage, ensuring a rail-to-rail voltage swing. While schematics represent this load as a discrete capacitor, modern integrated circuits rarely contain such components between logic gates. This symbol is a mathematical simplification of several parasitic physical phenomena that appear whenever transistors are interconnected. These complex parasitic values are embedded deep within the physical architecture of the downstream MOSFET being driven by the inverter. The gate electrode and the silicon substrate act as conductive plates, separated by the thin silicon dioxide dielectric layer. The base gate oxide capacitance is calculated from the thickness of the oxide and the physical dimensions of the gate, its width and length. Unlike a standard capacitor, the conductive channel forming the bottom plate physically changes based on the applied gate voltage. In the cutoff state, the transistor is off and the channel is absent. The gate capacitance is coupled directly into the deep bulk substrate. As voltage increases, the transistor enters the linear state. An inversion layer materializes, creating a conductive channel that bridges the source and the drain. Because the channel now connects to both terminals, the gate capacitance is effectively equally distributed between the source and the drain. In the saturation state, the voltage differential causes the channel to physically taper, eventually pinching off before it reaches the drain. This pinch-off effect isolates the drain, concentrating approximately 2/3 of the total gate capacitance onto the source terminal. Consequently, gate capacitance is a dynamic variable that shifts the electrical load as the transistor moves through different operational regions. Other parasitics reside at the physical boundaries where the gate edges meet the doped source and drain regions. During fabrication, high-temperature doping causes lateral diffusion. The source and drain regions spread horizontally, slipping slightly beneath the gate oxide. This results in a fixed electrostatic connection in these overlapping regions, known as overlap capacitance. This overlap is particularly impactful at the gate-to-drain boundary due to its effect on switching speed. This is a result of the Miller effect. This overlap capacitor effectively bridges the input and output of the inverter, creating a feedback loop. Since the output moves in the opposite direction of the input, the voltage across this capacitor changes by twice the supply voltage, significantly increasing the effective load. Even microscopic structural overlaps can therefore lead to a massive, disproportionate decrease in the inverter's maximum switching speed. Beneath the gate, the source and drain diffusion blocks are embedded in the deep silicon of the substrate. Each diffusion block forms a PN junction where it meets the differently doped substrate. In digital circuits, these junctions are reverse biased to prevent current from leaking into the substrate. This reverse bias creates a depletion region, a zone devoid of mobile charge, that wraps around the diffusion block and isolates it from the substrate. This insulating depletion region acts as the dielectric of a capacitor, forming what is known as junction or diffusion capacitance. The width of this region is nonlinear, changing in response to the voltage at the drain terminal. As voltage increases, the depletion region widens. This increased distance between the conductive regions results in a lower junction capacitance. Accurate modeling of this effect requires calculating the capacitance across the bottom area of the diffusion as well as the varying perimeter of the sidewalls. Ultimately, this creates a highly nonlinear, unpredictable electrical load that shifts and morphs constantly throughout the entire duration of a logic transition. By combining all of these physical observations, we can finally construct a comprehensive model of the inverter's entire electrical environment. The generic load capacitor symbol is replaced by its physical constituents, a lumped network of gate, overlap, and junction parasitics. Some of these parasitics are intrinsic to the driving gate, including its own internal drain junction and overlap capacitances. The remainder of the load is contributed by the next stage in the logic chain, primarily the gate oxide capacitance of the following transistor. A logic transition is the systematic management of these combined charges. The drive current must fill the gate oxide of the next stage, while overcoming the feedback of the Miller effect and the shifting widths of the depletion regions. SPICE simulation models utilize these physical parameters to calculate timing and performance with high precision. This highlights the central trade-off of design: increasing a transistor size to provide more drive current simultaneously increases the parasitic capacitances it must overcome. Effective integrated circuit design is the engineering of these physical capacitive mechanics.